So today, as we had to start this week's syllabus, we had already discussed yesterday papers and everything. Yes, Rudraksh, no, not Rudraksh. Someone asked na, that key change to that one PTA question was 6 to 4, 4 to 6, something was there. I think it was not, it was some A se naam tha. Aditya, was it you? Aditya, yesterday you asked na that
Yes, ma'am.
he has. So Aditya, wo that 4 came, I retried. There is some possibility of intramolecular attack, fiddlecraft type kuch hai kya on
Huh.
ring. I think that is why they have.
But will that form an alkene product? Alkene
The,
product, sorry.
yeah, better product is of course what we have done,
Huh.
but due to that something they have, they might have given 4.
Yeah.
Okay, so I just tried it. Ki how could it be 4? So that is what I was getting.
Hmm.
So I'm sharing. You can try again, but
Yes,
6 is
ma'am.
anyhow there and will be there.
Yes,
So if
6 is
you
what I
have
got
done
to clear.
6, then it is fine.
Hmm.
Okay, Aditya?
Yes,
Anything
ma'am.
else from
Nothing much.
yesterday? Nothing? So let's start. So Grignard reagent. So when we talk of Grignard reagent is an organometallic compound. It is a compound in which the metal is directly bonded to carbon, and where carbon will have the negative polarity, either the del negative or the full negative polarity. So when metal is directly bonded to negatively charged carbon, then such compounds are called organometallic. See, organ and metal. But do not consider that organic compounds having metal is not organometallic. Like RCONA, ROLI, if I talk of these compounds, these are organic compounds with metals, but they are not organometallic compounds. For organometallic compounds, metal should be directly bonded to carbon. See, Franklin reagent in an organozinc R2ZN. Ferrocene, the one you see in coordination complexes, where the cyclopentadienyl ion is upside downside and Fe2 plus is sandwiched between the two layers of the cyclopentadienyl ion. So ferrocene, R2CuLi, which is called Gilman reagent, RNA, RLI, tetraethyl lead is a TEL, common anti-knocking reagent, which was once upon extensively used, but now when you go to petrol pump, you read that note is unleaded petrol. So they indicate absence of tetraethyl lead in it, RHgCl, and so on. So ultimately, organometallic, when metal is directly bonded to carbon, then it is called organometallic compound. Okay. Now, when metal and carbon bonds are there, then certainly it is going to be a polar covalent bond. It is not possible for carbon to have a full ionic bond. So it is going to be a covalent bond. But due to electronegativity gap between metal and carbon, it is going to be a polar covalent bond. And with increase in electropositive nature of the metal, the polarity of that bond will continuously increase. Ionic nature of this bond will increase. And as this polarity increases, the ionic nature increases, the carbon cannot get hold of that polarity or cannot be stabilized with that polarity. So it becomes more and more reactive. So more the ionic character in this metal carbon bond, unstable the organometallic compound will be. Okay. Electropositive nature of metal, ionic nature of this bond increases and reactivity of organometallic compound increases. Now, ionic nature, which is observed in these organometallic compounds, is like sodium, then lithium, then magnesium, aluminium, zinc, cadmium, mercury. This is the order. Okay. With sodium and lithium and potassium, it is found to be primarily towards ionic. Okay, they do not have even that polar covalent structure. They are primarily ionic bonds. And when they are ionic bonds, that is why in Wood's reaction, you could never isolate RNA. You have an entire chapter dedicated to Grignard reagent. Grignard is something that you can prepare, you can isolate, you can use for other conversions and all. But for RNA and RK and RLI, we don't have any such possibility that we can separate them out and prepare for some other synthetic uses. When I talk of magnesium and lithium, these bonds are relatively less ionic. Yes, they are polar and polar covalent, yes, reactive, but comparatively, if I'm talking with respect to sodium potassium, it is relatively feasible to prepare them. And then comes the last ones, which are much more covalent, though polar covalent, but much more covalent and can be much easy to handle and store, prepare. That is why tetraethyl lead was added to petrol. Na? It was like so stable. Okay. So with decrease in electropositive nature of metal, the organometallic compound becomes relatively stable and can then be handled with much ease. Okay, but when I say handle, yes, you can prepare and store, but for conversions, for synthetic purpose of those other organic compound, we need a balance of stability and reactivity. If it is way too stable, it may not be sufficiently reactive. Too reactive, then definitely very limited applications and use would be there. So that beauty of reactivity and stability is given to us by magnesium. Okay. Synthesis of organometallic compounds. सबसे पहला first method of synthesis of organometallic compound is transmetallation. Transfer of metal, exchange of metal is the meaning of transmetallation. And the key here is a more electropositive metal from organometallic compound will be displaced by less electropositive metal. That is the rule. The more electropositive metal will displace less electropositive metal from the organometallic compound. So more electropositive metal, for example, if I have, say, this RLI, this behaves more electropositive than magnesium. So if I treat RLI with NgCl2, I will get RMgCl. If I treat RMgCl with CuCl, again less electropositive copper will displace magnesium and I'll get R2Cu. First I'll get RCu, but as copper is a d orbital, d block element, then again R minus will attack and R2Cu minus is formed. If I treat RMgCl with PbCl2, then I'll get R2Pb. Now, lead being plus 2 will disproportionate to R4Pb and lead. Okay, because with this, it is forming plus 4 stable. So, reactivity of organometallic compound depends on polarity of the carbon-metal bond. The greater the polarity of the bond, the more reactive the compound is as nucleophile. Bond polarity depends on electronegativity differences. And now when we say it depends on differences, I think you can easily estimate. You need not to have the exact values. A rough estimate of metal and the carbon difference we want. Okay. Second method is from alkyl halides. Like one is from one organometallic to another. Second is from alkyl halide. If we want to make it from alkyl halide, then how we can make Grignard reagent RMgX, where we add magnesium. And in dry ether, now if it was sodium, I would have had directly the coupled product, R and R combined. But here I'll get RMgX, okay, where magnesium gives 2 electron and form Mg2 plus and 2 electron. These 2 electron goes to R del plus. R minus is formed. Okay, what is formed? See, R plus. You must be aware that if I have R plus radical and I add 1 electron, I will get R dot. And if on dot I further add 1 electron, I will get R minus. So here I am taking it as R plus. So I add 1 electron, I would have got dot. 2 electron, I have got minus. Now there is a charge balancer, this magnesium 2 plus, so we got RMgX. Now there is a reversal of polarity. See, carbon from plus is changed to carbon minus in the entire reaction. So such reactions in which there is reversal of polarity are called ampolang. What is it? The name ampolang, that is reversal of polarity. Okay, it is called ampolang. Note, cannot use non-polar solvents like N-hexane, cyclohexane, benzene for the reaction and preparation of Grignard. Why? Because Grignard is not non-polar. Grignard is a polar compound. And if something is a polar compound, we cannot have a entirely non-polar medium for it to dissolve. Okay, so that is why we cannot have a non-polar solvent to dissolve it. Is that clear? And thus we need solvents which are polar. Now the point comes, how much polar or how much active it should be. So basically the purpose of polarity for these Grignard is this type of solvation support to Grignard. See, Grignard is covalent but polar. Now magnesium has d orbital, has empty orbital, d orbital. So oxygen lone pairs, if I am using ether, then form a coordinate linkage to this magnesium, and that is how this soluble complex is formed. So we cannot use a non-polar solvent like these which have no lone pair. Cannot use highly polar. If I go for highly polar or protic solvents, then also there will be problem, because this RMgX can then react with those protic solvent as acid base reaction, or can then react with those polar solvents with some nucleophilic addition and so reaction. So this is why we have a very limited narrow zone of solvents to be used. So we are left with very limited solvents like tetrahydrofuran, diethyl ether. Diethyl ether, we write this DME, which is dimethoxyethane. See this. Okay, dioxane, pyridine, any 3-degree amine. See, all of them are somehow having lone pair, and that is why they are allowed to be used here as a solvent. So we want solvent which are polar but not protic, and the polarity should not be sufficient enough that it somehow reacts Grignard for polar reactions or additions. It is difficult to make organometallic compounds of vinyl halide and PHX due to high bond dissociation energy of CX bond in them. Their organometallic or Grignard can be made only using THF or 3-degree amine as solvent. Only when we use these type of solvents which can practically survive high temperature boiling or high temperature conditions, only then we can have preparation of Grignard reagent from such compounds which are having double bond with the vinyl system. That is a problem. Is that clear? So we have to be careful with what we need from a given compound, right? According to that, you have to decide the solvent. Solvent condition should be absolutely dry, because we are using magnesium. Magnesium is a S block active metal. If we are using magnesium, then magnesium with water will have MgOH twice and hydrogen, plus of course highly exothermic, so explosions will be there. So we don't want any water present in the medium. Total anhydrous conditions are to be maintained. If we have the same alkyl, R is same, then order of ease of Grignard formation is Ri will be formed fastest, then RBr, then RCl, and RF is the most difficult to form. Why? Because of bond dissociation energies. For same halogen, if the halogen is same, the order of ease of Grignard formation is सबसे easy is methyl, then ethyl, then propyl and so on. Right? This is due to the formation of carbanion as intermediate. So once we have a Grignard, how to use it, how to go for reactions. So RMgX can act both as a strong base. Why a strong base? See, it is a conjugate of extremely weak acid alkanes, or I can say hydrocarbons. So if I talk of alkanes, then roughly if I say pK is 50 ke aspas. Okay, its pK is, and of course ranging from 44 to 51. So I'm just saying that its pK is 50 or so. So definitely these are very, very strong as a conjugate base because the acid is extremely poor. And when it is having a R minus, definitely it can act as a nucleophile also. So we have two natures for this Grignard. One to act as a base, other to act as a nucleophile. Now, when it acts as a base and it is made to react with some active hydrogen compound, then we call the reaction to be double decomposition. And basically, we have acid-base reaction. As I said, this is a conjugate of extremely weak acid. So there is a large spectrum of compounds which can react with it as an acid. Water, yes, because just see the pK values. This is somewhere 15.75, I guess, or 15.7, you can say. Alcohol, around 16 or so. HCl, तो highly acidic हो गए. PHOH, roughly pK is 9 point something, or I can say 10, right? Higher than 10, of course, but still acidic. Amines. Pyrrol ka this H is highly acidic. So what happens is this R dash, we are giving this H. Every place we are having alkane and the others are forming conjugate. PHO minus, NH2 minus, RNH minus, and we are just writing it with MgX positive. That is all what we are doing, right? Acid-base reaction. But this liberation of RH can be used to make integer questions, or we can use it to estimate number of acidic H in the unknown compound. Okay, that I'll use after 2 minutes. Give me some time, then I'll add. Further, some more famous acids if I want to react with. See, you can have the reaction with furthermore relatively weaker acids. This cyclopentadiene, its pK is roughly 16, and aromaticity is the driving force why it will form the anion. Terminal alkyne, this H if gone, then RC triple bond CMGX RH. Okay, pK 25. Acids you already think is 4.75 to 8. Here, active methylene, pK is 8.8 to 9. It is somewhat like phenol. So if phenol was reacting, this will react. pK 10.7. Here one side impure carbonyl, one side pure. We are using active methylene site for acidic. RCONH2 pK above 15, but still for something which is conjugate of pK 50 is still going to behave much, much stronger as an acid. Nitromethane, alpha to nitro positions, pK is 10.2, highly acidic. Okay, if I have alpha to nitro position, then acidity is much high, and then we get this acid-base reaction. So 1 mole of RMgX consumes 1 acidic H. So number of moles of RMgX consumed per mole of unknown compound will give number of acidic H in that unknown compound. And this is the ground or the criteria for quantitative analysis of number of acidic H. And the reaction is called Zerevitnov's estimation. What is it called? Zerevitnov's estimation of acidic H. Okay, it is called Zerevitnov estimation of acidic H. See, this molecule has 3 acidic H, terminal alkyne, OH, SH. So if I add X moles of CH3MgPr, I will get 3 methane molecule. Okay. And if they ask 1 mole of this, X moles of this and 3 methane. So what is the number of moles of Grignard used? 3. 3 acidic H, 3 moles of Grignard is used. Right? That is how they can use. Which of the following alkyl halide could be successfully used to form a Grignard reagent? Now see, when Br is there and you have OH, acidic H, definitely this cannot be prepared, this cannot be used for preparation of Grignard. Same, I have acidic H. Okay. And similarly, if you move further, here I have NH2H. So these are all having acidic H. Only this one is not having acidic H, as this is 3 degree amine. No acidic H. Here you can form Grignard. So answer is C. An alkyne releases 2 moles of methane per mole of alkyne. 2 mole of methane per mole of alkyne on reaction with CH3MgX. It means the alkyne must be having 2 acidic H. And it is said, what is the structure of alkyne? Smallest possible. The smallest possible alkyne with 2 acidic H is terminal alkyne. I cannot do something like in intermediate there are long carbon chain, because smallest possible is mentioned. Otherwise, if this was not mentioned, then you can have multiple options for such alkynes. Okay. Next comes the Grignard as a nucleophile. When Grignard acts as a nucleophile, it can give 2 types of reaction: nucleophilic addition reaction or nucleophilic substitution reaction. Okay. So when it gives nucleophilic addition reaction, it is the addition on polar pi bonded systems like C double bond O, C double bond S, N double bond O, S double bond O, and all. All these are having nucleophilic addition reactions. Is that okay? So these type of reactions will be observed on polar systems. Now point comes, what is the reaction that we will observe? Yes. So first, on general carbonyls, if I talk carbonyl, I mean aldehyde and ketone. So see, nucleophilic addition on carbonyl compound. Nucleophile attacks, pi bond opens. Here, the hybridization of carbonyl is sp2. Here, when this reaction happened, the hybridization has become sp3, 109 degree, 28 minutes. So the bond angle seems to be decreasing from 120 to 109 degree, 28 minutes. Then we take help of water with H plus. So we have RC nucleophile HOH. Okay, this is what is formed. RC nucleophile HOH. This product is formed. Now see, if I talk of RDS, we had to see how much del plus is there. Higher the del plus, easier for nucleophile to attack, right? So that is for sure, that higher the del plus, easier it will be for system to attack. So with increase in del plus on this carbonyl carbon, rate of nucleophilic addition will increase. One more thing you should observe is sp2 to sp3. So with increase in steric of these alkyl, rate of nucleophilic addition will decrease. This tetrahedral intermediate decides whether reaction will take place or not. And now we add water. So it becomes RC nucleophile H and OH. This is the product. Clear? Now in RDS, hybridization of carbonyl carbon changes from sp2 to sp3. Bond angle are decreased from 120 to 109. Thus, presence of bulky groups on carbonyl will resist this decrease. So heavier the groups on carbonyl, or it becomes from aldehyde to ketone, rate of nucleophilic addition will go on decreasing. It is better if we have aldehyde to be added, or I would say smaller alkyl groups on carbonyl, then it is easier to have this reaction. Otherwise, we may find difficulty in addition, or rather, I should say, just a decrease in rate is there. Difficulty is to be estimated just with the rate thing, nothing more. Okay. So, as nucleophile has to attack on carbonyl, carbon del plus, therefore, presence of electron releasing groups on carbonyl carbon will decrease the rate and electron withdrawing group will increase the rate. Aldehydes will be faster to react than ketones, right? Stability of tetrahedral intermediate, if I talk, in ketones I have this, in aldehyde I have H. Bond dissociation energy of C double bond O is greater than 2 times of C single bond O. It always wants to go back to carbonyl. If there is any leaving group on tetrahedral intermediate, then reaction goes back to C double bond O bond. This I'll explain. See what I'm explaining. See OH minus attack, pi opens. Now what I have got as a result, I have lost C double bond O. I have got 2 single CO energy, right? So if I say C single bond O BDE is X and C double bond OBDE is Y, then Y is even greater than 2 times of X. So that is why it will always try to go back. OH is a reasonably moderate leaving group. So it leaves back and it goes to the aldehyde stage. Yes, Harsh, you are allowed to unmute. Kindly ask. Harsh wanted to ask something. He rose the hand, but I don't see him able to unmute. And the hand is also gone. So, okay, let's continue. So, I was telling ki Cn minus comes and can be forward, can be made forward because Cn is not easy to be a leaving group. Yes, it will leave. It will leave. So, reaction is reversible. But compared to OH, it is relatively poorer leaving group. LiLH4. Now my choices of leaving group is either hydrides or R minus. All 3 atoms attached are very bad leaving group as minus. So there is no leaving group, it is irreversible. Similarly, when I add R dash Li, then similar way, the choices of leaving group are not possible. So reaction goes forward. So whether the reaction on carbonyl will be forward or backward is entirely decided by the leaving group. Whatever is available over there, that decides the the addition will go forward or not. Okay. Addition of RMgX on aldehyde and ketone. So as we have seen that Grignard addition will be irreversible. It cannot go backward. So R dash RMgX is attacking. We have RCH2O minus MgX. Now there is no possibility of any further addition. In the last, you will come across something like this. Either you will say acidic workup. That means addition of H plus. You can have NH4Cl aqueous or NHCO3 aqueous. Any of these. Okay, then when they are used to protonate, we get RCH2OH. Now I'm writing here it is a primary alcohol with 1 step up. What does this 1 step up means? That if we compare the carbon from this RMgX and this RCH2OH, see this R is common. This R is coming from Grignard, but there is this one extra CH2 which came from formaldehyde. So with respect to Grignard, there is a 1 step up reaction. We have got primary alcohol with 1 step up. Okay. Then comes with other aldehydes. Same way you will have 2 degree alcohol. Now 2-degree alcohol, and in this 2-degree alcohol, one R is from Grignard, other R is from aldehyde. Same way ketone, we'll get 3-degree alcohol, 1 R from aldehyde, 2 R are originally of ketones. So what we have to prepare, which type of alkyls we need to introduce, that you have to keep on observing, deciding, and as per that you will have to select the possible choices of combinations to prepare the given alcohol. Okay, so that is our choice. But on that, there are questions. I will try to cover questions or at least show you the questions, that what type of questions have been asked. Okay. So till here, I guess is okay, but I have one. Yes, Sai Dhanush.
Ma'am, could you explain about the forward reaction and backward reaction, which you explained the
Of
previous slide? When the forward reaction takes place and when the
no, forward reaction can take place anytime when we do not have, rather, I think you should ask reversible and irreversible instead of forward backward.
yes,
So if I have any, this tetrahedral intermediate, you check, which you can form with all possible nucleophiles. Then you check what are the groups attached to this carbon besides O minus. If any of those three groups can act as a leaving group, whether a relatively weaker leaving group or a stronger leaving group, what are the choices you compare? If they can be leaving group, then oxygen will always go back and reaction will have the reversible nature.
even the attacking nucleophile can act as a leaving group.
Oh, certainly, yes. That is why cyanohydrin formation on aldehyde ketone is reversible. Aldol is reversible. Ammonia and derivative addition is reversible. Right? You have a long list of reagents or reactions on aldehyde ketones which are reversible. Attack of water on aldehyde ketone is reversible. Right? So based on what is available and can it act as a leaving group, that decides for reaction to be reversible or not on aldehyde and ketones. Is that absolutely okay? So I guess Sai Dhanush has gone on mute again. So let's move to.
Yes, ma'am,
Yes,
it's
Sai.
clear.
Clear? Okay. So now you can mute yourself. So let's move to next point. So this was RMgX on aldehyde and ketone. Now this is a very important reaction which is written here on screen. You can take the screenshot after clearing your screen properly. You know, these are 3-member ring. 3-member ring is always exception in its class. Like if it was cyclopropane, it will behave like alkene. If it is amine, it will behave like rather an acid, poor amine. Ketone, this ketone behaves like acid derivative. Why acid derivative? It is not just that Grignard attacks and we have simple addition. No, we will have the ring opening reaction like in acid derivatives. We always have some leaving group and this O minus reverts. So apparently there was no leaving group, R, carbon, carbon. But due to strain, ring undergoes opening. Right? See, 3 has got minus charge. There I have attached MgX. Now, as Grignard is still available because this all thing happened when we are still in the medium of dry ether. Still we are in the medium of dry ether. We have not moved out of the ether. So again, I have got a one more reactive site. So next molecule will re-attack on this ketone site. Finally, we'll add aqueous NH4Cl. Now see what is NH4Cl? NH4Cl is ammonia plus HCl. So we are having a mild acidic condition only, na? Right? NH4Cl will be ammonia plus HCl, तो उसका aqueous solution will be acidic, and then we are having this 3-degree alcohol. We can have this similar reaction with 4-member ring, but we will not have a ring opening. We will have attack. We will simply have attack pi open. That's it. sp2 से sp3 बने. That is all we'll have. We'll not further have the ring opening. RMgX, same with 5-member ring. We have the attack and the there is no leaving group, carbon, 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 no need for that strain of the ring issue. So we have simple alcohol. Very, very important, nucleophilic addition on RMgX, of RMgX on RCl. Now see, cyanides if are there. Okay, so they certainly have a simple del plus. And I can have R dash attack on this, RC triple bond when added. So RC R dash double bond NMGX. Right? If I add further Grignard, or rather if I want to add further Grignard, still it will not be added. Okay? Why? Because see, nitrogen is a second period element. And 2 minus charges accumulation on nitrogen is not possible. Right? Second period element, for them, the second electron affinity of oxygen is positive. So that is an indication how difficult it is for it to have next R dash addition. Is that okay? So therefore, this is not possible, not formed at all. Even when you take RLI, then also this is not formed. So any long time you keep it in the medium of Grignard, you will not have any further reaction. And therefore, at this stage, you simply undergo hydrolysis. Okay. And when you will make its hydrolysis, first, I will simply have acid-base reaction. Right? RCR dash double bond NH. RCR dash double bond NH. Imine is formed. But as you all know, imines are easily hydrolyzed under water condition. And this is the net you can do. Break the 2 bonds, OH, OH, dehydrate. But the mechanism is also given here. So again, medium is made acidic, NH2 plus. Again, you add water, right? And these are all reversible, right? That is a possibility that I can have backward reaction there. Now, once I have water here, it is OH2 plus. So there is a proton exchange, or from medium, I can get a proton. Okay, so there is this proton exchange. I have RNH3 plus OH. This oxygen goes back for the bond, and NH3 plus is now a good leaving group. I have a protonated ketone, which on losing H plus will form a ketone. So in short, all this thing, you can directly go for breakage of RC double bond N and forming C double bond O. So overall, if I see in this ketone, RCN, 1R came from 1R alkyl came from RCN, and 1 alkyl came from Grignard reagent. But the reaction is ultimately always giving ketone. You will not have alcohols formed with cyanide. Okay, you will not have alcohols formed with cyanide. You will simply have ketone formed with cyanides. Is that clear? Yeah, very important. It is given in NCERT. It is extremely important reaction. Please remember, cyanide plus Grignard forms ketone, not any alcohol. Reaction stops at ketone stage. Now let us do few similar things. You can add further. If you add CO2. So, okay, CO2 added. First step, Grignard added. I will have RCOO minus. You may be tempted to add further RMgX, but once this resonance starts, this carbonyl del plus is so suppressed that next mole of Grignard is difficult to add. Okay, so Further, if I want to add RMgX, it is difficult to add. So no further addition. Why? Because RMgX is not sufficiently ionic. If you had RLi, it will add further. Okay. See, even on carboxylate, RLi is adding. But on carboxylate, Grignard is not adding. Okay. And then with aqueous NH4Cl, we will have RCOH. RLi will have 2 moles added. Then we will have Li2O removed, or you can say hydrolysis OH-OH. So answers are ketone. Is that clear? The answers are ketone with Grignard, with RLi. And answers are carboxylic acid with CO2. Similarly, if you will proceed, RMgX plus SO2, you will have sulfenic acid, SO3, sulfonic acids. If you add same way on ketene, R adding on CO2, so on ketene. Okay, so you will have formation of ketone. And it is a fixed thing that CH3C double bond O comes from ketene and RMgX comes from Grignard. Okay. With carboxylic acid, I will have just acid-base reaction, nothing more. But if it was RLi plus carboxylic acid, you will have ketones because carboxylate is also attacked by Grignard, by RLi. Okay, Grignard plus oxygen. Now see, oxygen by MOT is a biradical, right? So there is an insertion of oxygen in between R and Mg. ROOMgX is formed. Okay, but the peroxy linkage is unstable, so it breaks. Here we have a nascent oxygen. This next nascent oxygen is attacked by RMgX. Okay, so I have got ROMgX, 2 moles. One is this ROMgX, one is this ROMgX, 2 moles. On addition of aqueous NH4Cl, I have got alcohol. Okay, so RMgX with oxygen molecule, we'll get 2 moles of alcohol. It is a method of preparation of alcohol. Now see, if we are asked to prepare MEET MEOH using Grignard, which of the following combinations are correct? Here we are not asked best combination or worst combination. We are simply asked which are the correct combination. So when they ask correct combination, you simply see methyl, methyl and ET. Here also methyl, methyl and ET. So A is correct. Similarly, methyl, ethyl and 1 methyl here. So it will be correct. 2 ethyl incorrect, 2 ethyl incorrect. So you just select. But if the same question would have been asked, which is the best method? Okay. If it was asked, which is the best method? Which is the best method out of these? Then you will select A. Why? Because smaller alkyls on carbonyl, better nucleophilic addition than ethyl. Okay, best word usually goes for single answers. Let us go to next question. Abnormal behavior of RMgX. When 2 degree alkyl on ketone. Now ketone is having both side 2 degree. And alkyl of Grignard, all that is also 2 degree. Or it could be further bulkier. Then instead of addition, we have a cyclic redox. See, on this ketone, there is a pericyclic, that is cyclic transition state formation. This is my isopropyl. Oxygen going to magnesium. And we have a reduction of ketone to alcohol. And Grignard is converted to alkene. Okay, so we have a very different type of reaction. If we have crowded Grignard and crowded carbonyl, then you can have this reaction, though it is not very common. RMgX addition on conjugated carbonyls. If I have a conjugated carbonyl, that is this type. Now you can have possible attacks on position number 2 because of this resonating structure, or position number 4 due to this resonating structure. So there are two possible resonating structure. Nucleophile can attack at C2, or C4. RMgX preferably attack or RLI on C2, resulting in 1,2 addition as major product. This I am talking for J. For the chemistry purpose or for in general, there is a possibility that can there be 1,4 additions? There is a possibility. When it will be, how it will be, that depends. But for J, you can simply say RMgX or RLI, which are highly reactive, will attack on more del plus position. Okay, and you will have 1,2 addition product. If RMgX is placed with CuLi, okay, if you have the same reaction with CuLi, so basically RMgX with CuLi will form Gilman reagent in the reaction condition. It will form Gilman reaction. R2CuLi will form Gilman reagent in the reaction conditions. So RMgX plus CuLi, or directly if they give Gilman reagent, then we will go for 1,4 additions. See, 1,4 additions, and you will have carbonyl compound as a product. Is that absolutely clear? Please take note of this. Okay, with RLI and RMgX, for J, we take 1,2 additions. Until unless they mention directly in the question that take 1,4 addition. Sometimes in the question they write in the bracket 1,4 addition. Then we have to take. Otherwise, you have to take 1,2 addition. And with R2CuLi or with RMgX CuLi, you will have 1,4 additions. Is that absolutely okay? See? So that was all about nucleophilic addition reactions of Grignard. Now we are moving to nucleophilic substitution reaction. It can be on sp3 carbon, which is normal SN2 reactions, which we have studied last week. Yes, RMgX being a strong nucleophile. 1 degree, 2 degree, we will have coupling product. With 3 degree, it is difficult to have SN2 and we will have E2, elimination products. Right? That is what it is majorly obtained as. So that was about sp3 carbon. But what about sp2 carbon? In case of sp2, this substitution reaction we are talking is of SNAE, that is nucleophilic substitution through addition followed by elimination. SNAE, addition first and then elimination. Now what addition? This G group could be chlorine, then it is acid chloride. OR, then it is ester. OCOR, then it is anhydride, and NH2 when it is amide. So whatever I'm writing here is general, not for Grignard. I'm writing any nucleophile if attack. So if nucleophile attack, I'll have sp2 to sp3 change. Again, same thing. O minus will go back. Nucleophile can go back, then we'll go backward. G is gone, then you will have forward. And you have had G substituted by nucleophile. So it is nucleophilic substitution. RDS is addition. So through addition followed by elimination. Faster this addition, better is the rate of SNA. Feasibility of SNA will entirely depend on who will leave. If nucleophile is a better leaving group than G, then I'll say the reaction is failing. I'll go back to the reactant. And if G is a better leaving group than nucleophile, then we'll have forward reaction. Okay, if G is a better leaving group, then forward. If nucleophile is a better leaving group, then we'll have backward reaction. So that entirely depends what are these nucleophile and G. We have to decide that once those things are given in the question, that it will go forward or will go backward. Now, different types of RCOG could be chlorine, then anhydride, ester, amide. So based on the RDS, we want higher the del plus on this carbonyl, better the reaction will be. So RCOCl is fastest. Then comes the anhydride, then ester, then amide, and then carboxylate. Carboxylate will be the poorest of all, right? As the RDS is attack of nucleophile on RCOG, therefore with increase in del plus on CO, rate of SNAE will increase. More the del plus on this carbonyl, more will be the rate of this SNAE reaction. Take reaction of RMgX with different types of RCOG. Like I am exemplifying here with ester, but it could be acid chloride, it could be anhydride, like that. So let me start with ester. So I have ester. So first of all, I'm having a formic acid ester. So formic acid ester, if I have attack of R, I will have this type of intermediate formed. When this O minus reverts, ETO minus is gone. Okay, compared to this bond, I am having this as a leaving group. So aldehyde is obtained. So if I had 1 mole of Grignard addition, then I can have aldehyde. But if I had more mole of RMgX, I would have immediately here only added further Grignard. And answers will be 2 degree alcohol. But see the beauty, this time both alkyls are introduced by you. When you had the same 2 degree alcohol preparation from aldehyde, there you didn't have a choice. Am I right? There we didn't have the choice of what will be the alkyl introduction. I just had Grignard in my hand, so I had one alkyl to be introduced. If I want to introduce 2 alkyls which are identical, it is better to go by formic acid ester and Grignard reaction. You can have 2 alkyl introduction in your choice hand. If I had other acid, higher acid ester, then I will have ultimately 3 degree alcohol. So 2 alkyls will be from Grignard and 1 alkyl will be from original carboxylic acid ester. Okay. So it is again SNAE followed by nucleophilic addition. First there is SNAE. First ketone is formed and then nucleophilic addition. So 3 degree alcohol. Now here in cyclic systems, sometimes students make error. So be careful. And what error you can make. I can't say you will make, but a possibility is that you think that 5-member ring is now stable. So you should just add like this and close. No. 5-member ring is stable. That is an independent thing. But the functional group present will definitely have its own tendencies, its own reactivity. As the functional group once is ester, so it will continue to behave like an ester. Ester do not intend to give just addition. Na? It will have a return and O minus will leave. So don't think it is 5-member ring. Why is it opening? It is opening because it is not a hydrocarbon. It is having a good leaving group O minus. So it will 100% open like this. And then further you can have Grignard attack and thus see you have a 3 degree alcohol here and this original O is now part of this corner 1 degree alcohol. So just ring stable does not make a complete statement. What is the functional group of that ring? It will continue to behave with that functional group properties also. Just stable and close is not a right thing to say. Okay. Now 2 equivalent of Grignard if I am said. Okay. So first I'll say this acts pi open and this can attack like this intramolecular. I will have this. Right. But as it is said that if it is 2 equivalent further, and first I have had this is formed intramolecularly. Okay. But if I say 1 more mole of Grignard is there, CH3 MgX, then I can have again attack and open the ring. So you will have OMgX, double bond O, CH3. If they would have given more, I could have attacked more, but it was just a case of 2. So if they give 2 equivalent, then this type will be my answer. Okay, and followed by aqueous NH4Cl. If they have NH4Cl aqueous, no problem. We will have this to be OH. These are carbons. Huh? Clear? This step clear? Intramolecularly O minus, right? This is CH3 MgX. This attacked pi open. O minus is attacking intramolecularly on ester. Okay. See, 1 mole, if only 1 mole is given. So you open this ketone. O minus intramolecularly attacking Williamson. Alkoxide is attacking RCl. Williamson ether formation under ring is formed. How to decide whether to attack on carbonyl or RCl? So nucleophilic addition is faster than substitution. Therefore, addition is taking place first. Absolutely clear? Relative reactivity is normally acid-base react faster, then RCOCl, then aldehyde, ketone, anhydride, ester, alkyl halide. This is the order of reactivity of different functional groups towards Grignard. Okay. When I talk of ketones, like I have written aldehyde ketones acid base. So you may think that nucleophilic addition is taking place and this type of product is formed. Okay. What if I have NOH ka attack and this type of gemdiol is formed? Then this is major. Well, this was unstable, so you are getting this type of product. That is acid base. Here, when this attacks, this is irreversible. So kinetically, this is faster. Attack of Grignard on carbon plus is faster than abstracting that alpha H. So that is why we have a nucleophilic addition on aldehyde ketone. If there was no scope of such nucleophilic addition, then acid base will dominate. See here, much acidic, right? So here we have acid base reaction, not any nucleophilic. And once this minus is formed, do not add any further Grignard. Okay, this will now behave like carboxylate. Due to this resonance, both carbonyl del plus is suppressed. So you will not have any more addition of Grignard on this. Here the reaction will stop at this acid base reaction only. Then comes one of the past point, steric repulsions. We have done in carbocation also. CME3, CME3, CME3. Okay. So that is due to steric, this form carbocation faster than this. Anyways, it will come to your notes, you can see. Now that was SNA. I have exemplified with esters. You can have it on anhydride. You can have it on acid chlorides. But amides, no. In the amides, I have initially only shown you, I think, what should I say? Very, here. See, amides, you cannot take this type of reaction. In amides, it is acid base. Okay. For all others, it is what we were doing. That is a nucleophilic addition followed by elimination SNAE. Okay. Then comes the SN2 of RMgX on ethers. Now, ethers do not have any good leaving group. Other way of converting this OR to be good leaving group is make some acidic medium, give some H+. If there was some H+, this will be protonated and alcohol could be the good leaving group. But if there was some H+, instead of this R dash could have attacked. So I cannot carry out the reaction in acidic medium. And in basic or neutral, this cannot have a good leaving group and therefore ethers are unreactive to Grignard. And this is why we use them for the solvents of Grignard reaction. If it was reactive, then we would not have been able to use it as a solvent. 2OR, still no reaction. That is why acetals are used for masking in case of aldehyde ketone, because then I can have this thing that they are unreactive for attack of Grignard. right? Then comes 3OR. So if now I see I can have attack of one Grignard when there are 3OR, one Grignard attack is formed, just one. Then whether you keep it for infinity in Grignard, no further attack. So lastly, I'm taking in hydrolysis. 2OH will be there and ketone is formed. This is acetal. Hydrolysis will regenerate ketone. Okay, so SN2 of RMgX on ethers, you have ketones formed. Okay? Cyclic ethers, particularly 3 and 4 membered rings, react due to strain with RMgX. Otherwise, no. 3 member opens by SN2. So if there is a choice, less sterically hindered site will be attacked. And you will have 2-step up and 1 degree alcohol, primary alcohol is formed. Right? So we have primary alcohol formed with 2 steps up. If I had substituted ether like oxyrane, okay, see SN2, so I am having it less sterically hindered. Then open, you have a 2 degree alcohol formed. Okay, when I have 4 member ring oxytane, then when I attack, I have this type of ring opening. I have 3-step up primary alcohol is formed. ठीक? Tetrahydrofuran. Now ring is stable, no reaction. Therefore, THF is a solvent of Grignard. Correct? Some unusual reactions of Grignard, like when there is CH3ONH2. So definitely first is acid base. So I took acid base. RH is released. Now Grignard can attack. Right? And this is pretty much similar to like peroxy linkage thing that we did it, addition of oxygen. So see this and this. So we have CH3OMgX and RNHMgX. Hydrolysis, methanol and RNH2 is formed. So it is a method of preparation of rather primary amine. CH3ONH2 say we have got a primary amine. Chloramine, ClNH2 say also you are getting primary amine. Will there be acid base? Yes, same mechanism you can repeat for chloramine and you will have RNH2. Okay, so an important conclusion with these all functional groups, we cannot prepare Grignard because they will react with Grignard. Acid base, nucleophilic addition, substitution. Okay, acid base, nitro alpha H, acid base, nucleophilic addition, SN2. And this is not just it. There can be more functional group, but the point is all these will give some reaction with Grignard. So if they are present in the original compound, we cannot use for Grignard preparation. Important point to remember, RLI reacts with carboxylate, RMgX do not. Okay. RCOCl with organocadmium will form ketone. Okay. Ketones do not react with organocadmium. That is an important point. RCOCl react with R2COCl and ketones are the final product. No further reaction. This second and third reaction are given in carboxylic acid aldehyde ketone chapter. NCERT aldehyde ketone chapter. So there you will come across this. Now the type of questions that we expect in any exam on Grignard is, first is how many moles of CH3MgX will be consumed per mole of following compound. That is the first type of question. See, so you have to scan the entire molecule. And if there is acid base, include that. If there is any SNAE, nucleophilic addition, you have to add all types. So see here, only nucleophilic addition and 2 moles on acid derivative, so 3. Here, I can have similarly 2 and 1 and 2, 3. No. But the thing is, one, it is active methylene. I will have just one acid-base reaction and then no further reaction of Grignard. So answer is 1. Okay. Now coming to these. Now what happens? Sometimes now these questions, and let me write it my way. For example, if they say this reacts with X mole of CH3MgX This is given first. And then second, NH4Cl aqueous is there. Product they are saying. Let me write the product. OH, SH, OH, CH3, CH3, OH, CH3, CH3. Okay. So what will be the number of this X? What will be the value of this X? Several students see there is CH3 here, CH3 here, CH3 here, CH3 here. So answer is 4. No. You may think that here to H hai na, so there was no Grignard consumed. That is a wrong concept. 2 Grignards were consumed here. Total answer you will report this given product also 6. Grignard was consumed, but NH4Cl when came, then this H reappeared or re-added. That does not mean that we didn't lose mole of Grignard for this reaction. Is that clear? So even if they write this way, you should be smart enough that, okay, it was used and now they are again regenerating those H by NH4, so Cl aqueous. So still answer remains 6. Okay. So that was one type. And other type of question could have been like, what is the product form? That we can discuss later. First, there is a doubt. Yes.
Ma'am, why is there only 1 mole of Grignard reacting in B?
Because once that anion is formed, that active methylene anion, which is minus COOET, then due to this resonance, the del plus of both the carbonyls is depleted, is decreased. So like carboxylate, we cannot have next mole of Grignard attacking on these positions.
Okay.
Okay, Sai Dhanush?
Yes, ma'am.
Ekansh, allowed you to unmute. Please unmute. Yes.
Ma'am, in the third one,
Here.
isn't there a possibility of NGP happening between the SH and OH?
No, better not possible. Like which will act as a leaving group? For
Or the OH?
NGP, OH is a very bad leaving group. OH will leave only when it is protonated. And we cannot have H plus, otherwise Grignard will be lost.
Ma'am,
Okay,
but the NH4Cl
that
can provide an
that
uplift.
that all things are when you treat it with HBr and all. Here it is not sufficiently acidic to protonate OH. pH will not be that high, or rather I should say so low to protonate
Okay.
OH and make the reaction.
Okay.
Is that clear?
Yes.
Okay, anyone else with Grignard doubts, please raise your hand, then we'll talk to next topic. I think that is about Grignard. Okay, I have one more hand. Yes, tell.
When you told the priority about the reaction of Grignard, what if there are like groups of sulfur also? Then how will the priority change?
Groups of sulfur, if is acid base possibility, then it will go into this list.
What about SO3H or?
SO3H will give acid base, topper.
Okay. Any other groups of sulfur?
Do
Like,
not have those reactions in our syllabus as such. We do not take them into this reactivity order.
okay.
Yes, Ashish.
Ma'am,
Hmm.
ma'am, what is the, how do we differentiate the, when the reaction should be the nucleophilic addition on the substitution, nucleophilic substitution?
Nucleophilic addition or substitution?
In the reaction, how we can identify?
Well, I think we have covered it in the entire lecture, Ashish. You have joined from the start or not?
Yeah.
Please be louder.
Yeah, ma'am.
You were from the start of the lecture?
Yeah.
So we covered na, ki when there is aldehyde, ketone, cyanide, then it is nucleophilic addition. If they are acid derivatives, then it is nucleophilic substitution on sp2 carbon. If it is alkyl halide, then nucleophilic substitution on sp3 carbon.
Okay.
Right? We did it. You can have the recording on the notes and we'll find it.
Okay, ma'am. Thank you.
Yes, Ekansh?
Ma'am, in the place where you showed what and all react, like with Grignard reagent.
Please repeat.
Ma'am, with Grignard reagent,
Yeah.
you showed a list where all oxidants
Okay.
and all this are
With
there.
what you cannot form, you mean to say this, Ekansh?
Ma'am, the NO2 part.
NO2 part. Here is NO2.
Ma'am, you said that Grignard reagents, I mean, it's written that Grignard reagents cannot be prepared in the presence of these groups because they react with these.
So you want to say what is the reaction with NO2 part? That is what you are
Yes, ma'am.
asking.
Yes,
Beta,
ma'am.
that was acid-base reaction. Let me show you. Ruk. See? कहाँ गई वो NO2 वाली? ये रही. Okay, alpha 2 nitro is acid base. याद
Okay.
आया?
Yes.
I think Ekansh, your assignments and batch 2 assignments are similar or different? Hmm? Okay, I have allowed you to unmute again. So their
Ma'am,
assignments are same.
I
Same or
haven't
different?
read the assignment, ma'am. We just
Okay,
got
I
it today.
saw when I visited your center just last week, I had the same question, number of Grignard on someone asked the doubt from assignment. So there I remember they were doing just one less and that was alpha to nitro they were not including. So that is why I want to remind you that this was one question there. Okay.
Ma'am, so that's a key error?
What was the key? I think key
No, ma'am.
was 8 and he was saying 7. What did you say?
Ma'am, you said that in our assignment they did not include this one.
No, not the key person, the child who was asking.
Oh, I'm not
He
really
did
sure.
everything. He just was having one value less than the answer, and that was due to this alpha H. So
Okay.
now it should be in your mind because if it is
Yes.
there in your note somewhere, it must be there. Okay. So
Yes,
alpha
ma'am.
H acidity is used for nitroalkanes. Okay.
Ma'am, is this the only case of alpha H or are there any other cases?
Give me 1 second. Usually with alpha H, if you consider this also as alpha H, then active methylene will also be taken, na? Sudhamsh. Sorry, Ekansh.
Yes, ma'am.
Right?
Except active methylene and that.
So see, na, active methylene groups will be used for acidic H. Amides will be used for acidic H. These are also alpha H only.
Okay.
They could be there. Huh?
Yes.
So
Ma'am,
Nagaraj,
why does Grignard reagent not react with THF?
with?
THF, furan tetrahydrofuran.
So what type of reaction you expect of Grignard reagent with THF? Then I'll answer. What type of reaction you are expecting with THF? You tell me, then we'll answer that why that reaction is not happening.
The ring can expand? Or?
The ring can open, but it is already a 5-member ring. Why would it react? All these reactions were ring opening reactions, as it is not a good leaving group. There has to be driving force for ring to open, na?
Yes.
It is not there. Right?
Yes.
So that is why we cannot have that reaction. Anyone else? I have one hand. Rohit. Yes, Rohit, I have allowed you to unmute. Please ask.
Yeah, hello, ma'am. RMgX with HCN, what would happen?
Did you say RMgX with
HCN.
HCN? Some people incorrectly refer it as aldehyde formation, right?
Yeah, so it's acid-base reaction, right?
It should be acid-base reaction. It should not be taken as a preparation of aldehyde.
Okay.
It should be taken as acid-base, Rohit.
Okay, thank you.
Right? Okay. Anyone else with Grignard? Any more doubts? No one? Okay, I see one more hand. Sarvesh. Yes, Sarvesh. And
Ma'am, can you explain the solvents that we should use for Grignard reagent?
the solvents which were used for Grignard.
Yes, ma'am. Also the reason for their use.
Also,
The reason why we are using it.
as we said that we need lone pair donations for magnesium to keep it dissolved. It is a polar compound. It cannot be soluble in totally non-polar solvent like dissolves like. So if it is a polar compound, I cannot use a totally non-polar solvents, and I need something which is balance of polar and still non-reactive to Grignard reactions. So as we have seen by the end of the lecture that most of the things somehow react with Grignard reagent, either by acid base or by nucleophilic addition substitutions or any type of reaction. So by that logic, we are left with only these many reagents to be used as acid Grignard solvent. Okay. Okay, so that brings us to the Sarvesh, you were asking something more?
No, ma'am.
Okay, so then, okay, lower your hand. So there is, okay, one more hand is there. Let me ask. Yeah, please tell.
Ma'am, you told that R2CuLi shows 1,4 addition and Grignard reagent does not show 1,4 addition. Can you tell why that happens?
That is beyond the time allotted at this time. You have to refer your phase 1 notes for that. Okay, that is a big point of discussion, like how and why. That is beyond the time that we have. Refer your phase 1 notes for that, please.
Yes, ma'am.